Okay, so although this sideways parabola is not a function, we'll actually find in example 3 that it is two functions stuck together. But we'll come back to that later. For right now, let's talk about the horizontal line test, which is stated on page 148 by saying if the graph of a function y equals f of x is such that no horizontal line intersects the graph in more than one point, then we say that this function f of x is one-to-one, and it does have an inverse. So that implies that if the graph of y equals f of x, like this red parabola, fails the horizontal line test, then I know that that f of x is not a one-to-one function, and that means that the inverse is going to fail the vertical line test, so the inverse is not a function. I don't care how you write the horizontal line test into your notes, in whatever way makes the most sense to you. You don't have to write it exactly the way it's stated in the book right here, but just make some kind of note as that the horizontal line test of a function implies that the vertical line test will fail on the inverse, and it's not a function. Our book will tell you that if a function is not one-to-one, then the inverse does not exist. We're going to use the same equation that we used in example 2 for example 3. So it's a parabola. However, we knew the inverse was not a function because this was not a one-to-one function. However, if we restrict the domain to values of x greater than or equal to 0, then we'll have a function that's one-to-one. We'll take a look at the graphs to verify that. This was the graph from example 2, and that fails the horizontal line test, so there was no inverse function. However, restricting the domain to x coordinates that are greater than or equal to 0 will just result in the right side of the parabola, and that passes the horizontal line test. So the inverse function does exist. So for example 3, we're going to sketch a graph of the inverse function, and we're going to find a rule or an equation for the inverse function. So part A, sketching a graph, requires two tables of value. Even though I didn't put the heading here, this table will be points on the graph of f of x. So on the graph of f of x, we already have some points. We did that in example 2. When x is 0, f of x is 4. So 0, 4 is on this graph of f of x. That means 4, 0. Swapping the x and y coordinates will give me a point on the inverse function. 1, 3 is on the graph of f of x. That means that 3, 1 is on the graph of the inverse function. Notice I'm only using x coordinates that are 0 or higher. 2, 0 is on the graph of f of x, meaning 0, 2 is on the inverse function. And we knew that 3, -5 is on the graph of f of x. That means that -5, 3 is on the inverse function. So graphing the f of x equals 4 minus x squared with the restricted domain results in this graph. And the domain of this function is x is greater than or equal to 0. Notice that that's now the range of the inverse function. So I can only get y coordinates that are 0 or higher. So I'm only getting the top half of the sideways facing parabola that we had for example 2. So what we have here is that the domain of f of x is greater than or equal to 0, now becomes the range of f inverse of x, y is greater than or equal to 0. Also, the range of f of x is y is less than or equal to 4. We can tell that by looking at the graph too. All the y coordinates on this function, f of x, start at 4, and they're anything less than that. Notice that that's the same as the domain of f inverse of x. So all of the x coordinates on the inverse function start at 4, and they get smaller and smaller. So the range of f of x, y is less than or equal to 4, becomes the domain of f inverse of x. X is less than or equal to 4. And we'll see later when we come up with the equation why this is also true. Notice that the graph of f of x reflected over the line y equals x will result in the graph of the inverse function. Now let's do part B for example 3, finding a rule for f inverse of x. Just like we did in the other example, we're going to start by replacing f of x with y. So we'll have y equals 4 minus x squared. Next, we swap x and y to get x equals 4 minus y squared. Now I'm going to solve for y. And I'm going to start doing that by subtracting 4 from each side of the equation to get x minus 4 equals negative y squared. What I need to do now is change the sign of both sides. So multiplying each side by negative 1 will result in negative x plus 4 equals y squared, because minus negative 4 when I distribute the negative sign will give me positive y squared. That's the same thing as positive 4 minus x. I just wanted to make the illustration that changing the sign of a subtraction problem, that's just what I did here. I changed the sign of both sides, results in subtraction being done in the reverse order. So the opposite of negative y squared is positive y squared, but the opposite of x minus 4 is 4 minus x. Now I'm going to solve for y by taking the square root of both sides, and normally I would have to take the positive and negative square root of 4 minus x, but like we saw earlier, that's actually two functions stuck together. That's y equals the positive square root of 4 minus x, which is the top half of the sideways parabola, and it's also y equals the negative square root of 4 minus x, which is the bottom half of the parabola. And like I said earlier, this is two functions stuck together. But because we restricted the domain for f of x to get it to be 1-to-1 so that it would have an inverse function, we now need to restrict the the range of f of x. The range of f inverse of x. So we really only want to count positive y values on the inverse function, which means I'm not going to use this part of the parabola. I'm only going to use the top half of the parabola where the y values are positive. So that becomes my inverse function. F inverse equals the square root of 4 minus x. And if you recall earlier, we said that the domain of this inverse function was x is less than or equal to 4. And that makes sense because if I use a value of x that's more than 4 here, I'll be taking the square root of a negative number. And then the value f inverse of x would be a non-real number. So that's why it starts at 4 and gets smaller and smaller for values of x that I can use. Now let's do example 4. Example 4, let f of x equal the cubed root of x plus 4. We're just going to find the inverse function if it exists. And I'm going to see if the inverse function exists by looking at a graph of the cubed root of x plus 4. And it makes sense that when x is negative 4, f of x would be 0. So negative 4 comma 0 is on this graph. Negative 4 is the 0. Negative 4 plus 4 was 0. The cube root of 0 would give me 0. So there's your cube root function, and I can see that it does pass the horizontal line test, so the inverse does exist. It is a 1-to-1 function, so I can find the inverse function. So to find the inverse function, I'm going to go through all the steps again. I'm going to replace f of x with y to get y equals the cube root of x plus 4. Then swap x and y to get x equals the cube root of y plus 4. And now I need to solve for y. And I'm going to start solving for y by undoing the cube root by cubing each side of the equation. Don't forget that cubing and cube rooting are inverse functions, so they undo each other. So on this side, I'm just left with y plus 4, and on the other side, I'm left with x cubed. Last step, subtract 4 from each side, to get x cubed minus 4 equals y. So the inverse function f inverse of x is equal to x cubed minus 4. So for example 4, we know that f inverse of x is x cubed minus 4. And I always like to double check my work by taking a look at the graph of f of x, which is this red one, and the graph of f inverse of x, which is the blue one, and I can see that they are reflections of one another across the line y equals x. So graphically, it looks like it checks out. I also double check my work sometimes by plugging in numbers for x and f of x, and you'll see what I mean by that. So like for instance, I'll plug in 4 for x and find out what f of 4 is. I chose 4 because it's a perfect cube resulting underneath the radical sign. Because the cube root of 8 is 2. So that means that when x is 4, f of x is 2. So f of 4 equals 2. Now I can check to see if this is the right inverse function, then f inverse of 2 should give me 4. Reverse the input and output. So let's find out what f inverse of 2 is. F inverse of 2 would be 2 cubed minus 4, which is 8 minus 4, which is 4. So yes, f of 4 equals 2, and f inverse of 2 does equal 4. So it looks like I may have the right inverse function. Remember, this is a proof by example, which doesn't really prove anything, but it's a good way to check your work. So in conclusion, there are some things to remember from this lesson. One of them, if you need to graph an inverse function, make 2 xy tables. One for f of x, and then you swap the x and y coordinates to get points on the inverse function's graph. The second thing is if you're asked to find a rule for the inverse, that's just meaning you're asked to find an equation for the inverse function. Step 1 is to replace the f of x with y if it's not already done. Swap x and y, swap places, and then solve for y. And the result that you get for y will be your inverse function, f inverse of x. Another thing to remember is that if you need to verify that 2 functions are inverses of one another, then you need to do 2 function compositions. You need to find f of g of x, and you also need to find g of f of x, and they should both simplify to x. And the last thing, horizontal line test is what we use to determine if a function has an inverse that is a function. So if f of x passes the horizontal line test, that's what HLT is abbreviated for, then it's 1-to-1 and its inverse is a function.